Okay, so here's finishing up with the summing of the 1 over the reciprocal of the squares. So 1 over 1 plus 1 over 2 squared plus 1 over 3 squared and so forth. So what do? I initialize my sum as 0, and then I come in here and what I want to do is take whatever I have at this point, so that sum I have so far, and add to it my next term. And now the thing is again, this sequence here starts at 0, and so boy, if I had 1 over 0 squared, that would be an error. That would be a real problem. And so I just fixed that. Instead of starting this off at 1, which I could do, I started off at 0 and just add 1. So either of those cases would work. So, you know, I could have just as easily, I'll do this as a comment, I could have easily just said range, you know, so in range, and I could have started at 1 and gone up to n plus 1, I guess, and that would have stopped me at n. And then again, I could have added a comma and a 1, but it will do that on its own. So I could have used that instead of this, and then I would have just had I squared instead of I plus 1 squared. So I just had to make sure I had the right number that I was dividing by. And then, so I simply go through and I add the next one, you know, so n is 0, so I get 1 over 1 squared. I add that, so I'll have a total of 1. Then I go back here, I changes to 1, and so I'll get 1 over 2 squared, or 1/4, and so that will change and it will go through, and we can check these one at a time. So that was one way to do it, but you see I'm adding the biggest number, 1, and then adding smaller and smaller numbers. That's typically not a good idea when you're especially trying to add a bunch of numbers that are getting very small together. And so I also looked at it as I made a sum too, you know, so I started this one at 0. But now what I want to do is start at my biggest number, n, and go down to 1 and subtract 1. And do it that way. Now I chose to, you know, so this first one will be n, so I'll get 1 over n squared. Then the next one will be 1 over n minus 1 squared. That'll be the next number. So if n was, say, 5, this would start at 1 over 25, and then it would add 1 over 16 to that, or 1 over 4 squared, and then 1 over 3 squared, and then, now in my case, I stopped it. Actually, to tell you the truth, I'm not sure why I did this. Maybe I'll change it right now. But I stopped it here at 1, which means it actually stopped at 2. That was the last one. So it did 1 over 4 squared, or not 4 squared, 1 over 4, or 1 over 2 squared, added to it. But then here I added the 1. I don't know why I did that. I didn't need to. So let me fix that here. I can make that a 0. Now the last number we'll do is a 1, and I won't add the 1 out here. But you see, I could have. I could do it either way. And so I'll print these out. Now here I wanted to print the next term out that you would add. So, well, here's the next sum, and then minus the previous sum. And what I was trying to do is just eventually show that you are adding, you'll get down to where you'll the difference between the two numbers is 0. In other words, it's a problem. It won't know that you're adding this much, and that, again, that's the problem with adding biggest first and smallest last. So again, if we run for 1, we got 1 in both cases. The number we're looking for is 1.6493406 and so forth. So that was 1, so I should have gotten 1. And the next number should be 0.25 more that I add to that. And that's right, because that's 1 over 2 squared, or 1 over 4. And so if I change this to 2 and run it, then I got that 1.25 in both cases. And now this is supposed to be 1/9. It's off a little bit here because those should all be 1s, but again, that's what a computer does. And so I'm getting a little closer to what I'm calling the right answer. I went to Sage Math, which has some very good constants in it and so forth, and I ask it for pi squared over 6, which is what this adds to. And it says pi squared over 6 is this number here to this many decimal places. I believe it. And as we watch these numbers, we see that they get closer and closer for a while. I say for a while because this one up here, the one where we add biggest to smallest, stops getting closer. It just stops. So there's 2, here's 3, and I run that one, and you see they're both the same number still. You know, I'm looking here to see they're both the same number. 4, run that, and they are still both the same number. And I'm adding just 0.04 and then some stuff at the end. So now let me take it up to 10. Okay, and if you look, it looks like all the digits are the same. So all the way to 1 over 10 squared, or adding 1 over 100, I get the same answer. And it's getting pretty close to the right answer. But I need to go farther out to get closer to the right answer. Whoops, I didn't change anything. So let me try at 100. And what you see is at 100, all of a sudden, I get different answers. Now they aren't a lot different, right? They're only different way out here. And they're both getting closer. They're close. They're 1.6. They both got that right, but they would round to 1.63 instead of 1.64. But they agree pretty far out here. Now, if you go to 1,000 and run those, then you know what you see actually is they don't agree as far out. But they're both getting very close. These would round to 1.644. This one rounds to 1.645. Okay, so they're getting close, at least, you know, to the first 2 decimal places here. They're correct. At 1,000, if you go to 10,000. Okay, again, you see that they're different, but they're both getting much closer. They would both round to 1.645, which would be correct. Now, this decimal place isn't right. Well, let me add a couple more zeros to make it 1,000,000, and it takes a little longer to run, but it's not too bad. And at 1,000,000, so 10 to the 6th, again, you know, they agree pretty far out, but they disagree if it matters, you know, well, it matters. And, you know, but they both agree out to the 6494493. So 1, 2, 3, 4, 5 places past the decimal, 6 digits total, they agree. So that was a million. Try 10 million or 10 to the 7th. It starts getting a little slower, but I don't think it's so slow we can't wait for it. So yeah, wait for it, wait for it. There's one of them. And so that's at 10 to the 7th. And so we see they're agreeing, you know, they would, rounding, they would agree clear to here, 1.644934. So that would be what, 1, 2, 3, 4, 5, 6, 7 decimal places now. But we also see here, this is starting to get really close to where we aren't going to be able to see it. And I think it takes a while to run. I'll give it a minute and talk about the answer. But so if we go to 10 to the 8th and run it there, I believe what you find is now this will be 0. We'll see if it runs in any kind of decent time. But you'll see that if you add biggest to smallest, that when you look at trying to add the next number on, the computer will basically think you're trying to add 0. And that's a problem because it won't change the sum. And I've got some numbers here. I'll switch to the screencast view. Hopefully that'll do okay. Well, let me switch to that and then we'll come back to this. And see how delayed. Lecture. What we see at 10 to the 8th, okay, so if we add out to 10 to the 8th, the biggest first, with that, you know, forth. That up. Oh. Okay. First, you get 6449 and so forth. However, at that point, if you went to and I don't know what actually happens, but I can keep, and however, when we get I didn't check any bigger number than that because it took so long to run through this. That's a lot of numbers to add, 10 to the 10th, right? Because it's adding 1 over these numbers squared all the way to 10 to the 10th. So if you square that, you actually have 10 to the 20th as far as a small number. But even at 10 to the 10th, the sum kept changing, which is a good thing. Okay, so it kept changing, and it agreed to, let's see, 1, 2, 3, 4, 5. Well, it agreed down to the 6.6. So it said 1.6, and I have it actually on the computer. The one, I didn't erase that after I did it. It took a long time to do, but it was 1.6449306.7, and then some other stuff. The right answer, but so that was, how many digits? 10 digits? 1, 2, 3, 4, 6, 7, 8, 9, 10. So yeah, it agreed to 10 digits, was off by 1 in the 11th digit. So it was doing quite well, and like I say, it kept changing, and so that's a much better solution than if you had added biggest to smallest. And so yeah, here's where I did the 10 to the 10th. There's the number I got, and there's the 667, and it was up here, what we're calling the right answer was 668. And so you see, though, it kept changing as I added more and more numbers. But I think this took, gosh, how long did this take? This took like an hour to run, or something like that. It took forever. And so you see, I mean, it's not something you just willy-nilly do. And like I couldn't, I went to try to create your homework file. While this was running, it wouldn't even let me create a new file. So it was busy. It was very busy. But this is showing you then that if I try to add those 1 over k squared, k equal 1 to sum n, that you do get a better answer by adding biggest to smallest. Okay, so what I ask you to do in homework is instead of numbers squared, I ask you to add 1 over their factorial, and I give you a hint on that. So with that, I will conclude this video.